This video deals with the idea of Lorentz invariance and shows how an invariant scalar quantity can be formed from the contraction of certain four vectors. This contracted scalar quantity can then be shown to be unaffected by an arbitrary Lorentz transformation between inertial frames in constant relative motion. So Lorentz scalars are formed from the scalar product of four vectors. So one such four vector is a position vector. Its components x mu, each of the components time component x, y and z. Tau here is the proper time, so an object carrying its own clock will record proper time as it moves. Now the Lorentz scalar can be formed here, is x dot x, a scalar product of the position vector itself, written out components times the basis vectors, scalar product, and when we do that, we factorise out the basis vector part and the component part. These basis vectors here give us the eta mu, which is the metric for flat space, the Minkowski metric, times the components, and we use the Minkowski metric to lower this index, and then so we have one index down, one index up, so when we sum that out, we'll get a scalar expression. Now Lorentz scalars are invariant no matter what the value of the Lorentz factor, and we'll see that shortly. And the invariance of Lorentz scalars means that observers in different inertial frames moving with constant relative speed with respect to each other will always agree on the value of these scalars. And so let's have a look at this. Alright, now let's say we have two frames S and S prime, or S dash, are moving relative to each other in a common direction along the x prime axes with a velocity v as shown below. So here's our velocity v, s prime moving with respect to s. This configuration is also called standard configuration, and it's where we also assume the frames coincide at t equals t dash equals 0. So we have a frame s prime in relative constant motion with respect to each other. Now, both observers see the same event but ascribe different coordinates to it. So in the S frame, an observer here, the purple observer, sees an event and gives it coordinates ct, x, y, z, and the same event as seen by the blue observer in the S prime frame is ct dash, x dash, y dash, z dash. Now these coordinates are related by the Lorentz transformation. The Lorentz factor is given here by gamma is 1 over the square root of 1 minus v squared on c squared, or 1 on the square root of 1 minus beta squared, where beta is v on c. Right. So Lorentz factor or Lorentz boost, this frame S prime is moving with speed v with respect to s along the positive direction of both their axes, and the Lorentz factor in transforming from frame S to frame S prime is gamma here. This is the Lorentz factor. This gives us the boost and affects the coordinates, as we'll see shortly. Alright, so the relationship between these coordinates is given by, for a standard configuration here, ct dash, x dash, y dash, z dash will be this transformation matrix times ct, x, y, z. Now, what we're going to do, so that's how we take the coordinates here in the S frame, these ones, ct, x, y, z, and transform them to the primed frame, the primed coordinates in the S prime frame, and we use this transformation matrix which involves the Lorentz factor gamma. Okay, now our aim now is to square each of these coordinates, 1, 2, 3, 4, and then sum them, after which we will compare the resultant scalar formed for the S and the S prime frames. That is, we want to see what the space-time interval ds squared and ds prime squared produces for both frames. So an observer in frame S seeks ds squared, the observer in frame S prime seeks ds prime squared, and then we'll compare them. Alright, so here we go. We take ct prime with this object here, we can rewrite like this. Now if we square it, we get this object here, expand it out, and what we'll do with the gamma here, that's 1 over the square root of that 1 minus v squared on c squared, and when we do a little bit of algebra, rearrange that, we actually get this object here, c squared over c squared minus v squared times this object here. A little bit of common denominator c here, hence the c squared there. Okay, and then what we'll do is expand out the brackets. Here we go, and moving on to the next coordinate now. X prime is this object here, gamma times that, just rearranging it a bit, getting rid of beta, putting v over c, squaring it now, both sides. X prime squared is gamma squared times this object here, again expand it out, gamma squared is this part here, and then we'll just common denominator c here, and then we're left with this times this. Alright, notice in the y and z directions no transformation occurs because there's no motion in those directions, so there's no Lorentz transformation involved. Y dash squared is y squared, z dash or z prime squared is z squared. Next one over. Let's now combine these. Minus c squared t dash squared plus x dash squared is this object here. That's just collecting the terms we created earlier on the previous slides. A little bit of algebra here, dividing through by c squared on this one down the bottom here, and same up here as well. When we do that, we create these two terms here, and the next line down we can find the common denominator of c squared minus v squared, combine these two terms in the brackets to give us this, then we can factorise out, and this c squared minus v squared, and this also, this factor of c squared minus v squared over here will cancel out with the denominator, and we're left with minus c squared t squared plus x squared. So the space-time interval for the observer in S prime is this. The space-time interval, ds squared, for the observer in S is this, and they both agree that it's the same, they're equal to each other, independent of whatever Lorentz factor was involved. As you can see, there's no gamma involved in here. Alright, so both observers agree on the value of the scalar. The observer in the primed frame has this space-time interval. The observer in S has this space-time interval. They both agree with each other, quite independent of the Lorentz factor. The Lorentz factor could be anything. The end result is that these space-time intervals are the same for both observers. Now we can write this space-time interval as a difference of coordinates in the form ds squared is ds prime squared, so using the differentials there instead of the individual coordinates, we get this object here. Now we can use Lorentz invariance to learn something else about the line element ds squared. So let's just come back here now to our observer in S and our observer in S prime. This time now we're going to call the S prime frame the spaceship in which this observer is seated, and the rear end of the spaceship has a light that flashes right next door to the observer in S prime, who's sitting right next to the end of the spaceship there, and according to the observer in the spaceship, this is the corner, this is their axes, x prime, y prime, and according to them, this flash of light, which occurs at the origin of their coordinate system, has coordinate ct dash, which is c times tau. Tau is the proper time, that's the clock this blue observer carries, who is at rest with respect to the spaceship, because the spaceship forms the axes, the space-time, these axes here, spatial axes here. And so for this observer, their x, y and z are 0 because this light flash occurs at their origin. Frame S prime is moving with respect to frame S with speed v as before. The green observer in S now gives the light flash the coordinates ct, x, y, z. Now, the line element in this situation is given by, for the observer in S, this is their space-time interval for the event, and for the observer on the spaceship, the blue observer on the spaceship, at rest with respect to the spaceship, sitting at the end of the spaceship, sees this object here. That's their space-time interval. There's no x, y or z because it occurs at their origin. And so ds squared is minus c squared d tau squared, but we've already seen that ds prime squared is ds squared, and so we must have ds prime squared is minus c squared d tau squared. Okay, now that's going to be helpful because that means our first Lorentz invariant scalar is this scalar product for the primed observer is equal to this scalar product for the observer in frame S. So this is frame S prime, this is frame S. They both agree they're equal to each other, and they both agree it's equal to minus c squared times tau squared. So that's our first Lorentz invariant scalar. Notice there's no gamma in here. They're quite independent. Doesn't matter what factor gamma is. Alright, now for an observer in some frame S watching an object passing by with speed v, they will record the following components for its velocity. So an observer in frame S looks up and sees an object passing by and will ascribe to that object the velocity components gamma times dx mu dt, this object here. Gamma is the Lorentz factor here. The object is moving past a constant speed v, whatever that v is. Okay, now these can be written as v contravariant x, v contravariant y, v contravariant z. And then we take out the gamma factor out front and we can have c, vx, vy, vz. So a bit nicely represented. So our next Lorentz invariant scalar involves the magnitude of the velocity vector, which is also the tangent vector to the world line of the object. So we seek the magnitude of the tangent vector or velocity vector squared, which is the scalar product of the velocity vector with itself. Alright, v dot v, this object here dotted with that. Let's take out the basis vector again, which gives us the Minkowski metric, eta mu nu, times these objects here. Use the Minkowski metric to lower the index on the first object here, the first velocity component. And we get v nu times v nu, one lower, one upper, so we're summing that out. That gives us gamma squared, this object here. If you remember the previous page, what each of these components were, v mu. The upper ones were the vx, vy, vz up there and a minus c. And then the lower ones will be a c and, so again the upper component will be a plus c. Vx, Vy, Vz upper, and the lower one, by lowering it, we'll get a minus c factor, and then we'll have V lower x, V lower y, Vz. Now, this object here is just V squared. It's just the square of the speed. The spatial part here is just the square of the speed, so we have minus c squared plus V squared. We know from earlier that gamma squared is c squared on c squared minus V squared, and we multiply that out, but what we'll do is we'll rearrange this and put a minus sign in front, alright, so that we have c squared minus v squared in the numerator, c squared minus v squared in the denominator, and they will cancel, and we're left with just minus c squared from this scalar product of the velocity vector or tangent to the world line vector with itself. Alright, so our velocity vector involved the Lorentz factor gamma. V is this, remember this object here, gamma, that. Okay. We then formed a scalar that is independent of the Lorentz factor. This scalar product gave us this object here, which is just equal to minus c squared, no gamma factor in sight at all. So our next Lorentz invariant scalar is this object here. Doesn't matter what value gamma takes, the Lorentz factor takes, this scalar product of the velocity vector itself would just be equal to minus c squared, irrespective of what the velocity is. Alright, let's come at that from another approach now, using the space-time interval squared can also be written as, or the space-time interval can be written as eta mu nu, that's the metric, the Minkowski flat space metric, times these differentials here, and that's equal to minus c squared d tau squared. So in the last term here, why don't we divide through by d tau squared, leaving minus c squared by itself, and then underneath here, now just separate those two. Down here, d tau times d tau, which is d tau squared, and that gives us the component of the velocity vector, and that's also the component of the velocity vector, or the vector that is tangent to this world line of the object. So here we go, eta mu nu, v nu upper is minus c squared, but we can use that Minkowski metric to lower the index here, mu, and when we do that, we will actually down here, lowering that, using the metric here to lower that index will give us this one here, and again we have the same result, minus c squared. So the scalar product of the velocity vector with itself just gives us minus c squared. The observer in S determines, we'll move on now, the next example. The observer in S determines the momentum of the spaceship in S prime to be P is m0, v, m0, m0, the rest mass, v mu, the components, velocity components. Here's the basis vector. The components here separately are just this part here, and we can write that as this, expanding that out. Now, that can be rewritten as m0 gamma c squared on c, which is the energy, the top part here, in the numerator. M0 gamma c squared is the energy of the object, total energy. And over c, here's the individual components for the momentum. Alright, and all of that can be written as E over c, px, py, pz. Now, the magnitude of this momentum is, the magnitude squared, I should say. It's the momentum vector, scalar product of the momentum vector with itself, gives us this object here, which is this. And as we've seen, v dot v is just minus c squared. So what we have is minus m0 squared c squared. And again, no presence of gamma in here. Alright, now we can also find it by p dot p is, again, using the metric here. We'll lower that index. That becomes, so doing p lower with p upper gives us this object here. And we can rewrite that. This is just the square of the momentum, p squared. Now, from these two approaches we can see that this last object here is equal to this. Now if we multiply through, just to make it look a little bit more pleasant, we just multiply through everything by plus c minus c squared. We can have e squared minus p squared c squared is equal to m0 squared times c to the power of 4. And notice there's no gamma in here. Alright, so all observers in relative motion with constant speed with respect to each other, i.e. S and S prime, agree on the value of the rest mass m0 and the value of c. That means they also agree that e squared minus p squared c squared, that's the observer in S, records this scalar. The observer in S prime records this scalar. And they both agree with each other, simply because, if you remember earlier, this minus m0 squared c squared, there's no presence of gamma, and all observers agree on the value of the speed of light. All observers agree that it is 3 times 10 to the 8 meters per second, and all observers agree on the rest mass of the object. And so this scalar, that's what the observer in S records, is the same as what the observer in S prime records. So this is another example of a Lorentz scalar that is invariant under any Lorentz transformation. So some examples of Lorentz scalars include position vector dotted with itself, the scalar product position vector with itself is equal to this object. The velocity vector, which is also the tangent vector to the world line of the particle, the scalar product of that with itself is this. And the momentum vector is this. Now, it turns out also that the velocity vector and the acceleration vector are always going to be orthogonal to each other, so they're always going to be 0. The D'Alembert operator, this object here, again is another Lorentz invariant scalar. And that means nowhere does a Lorentz factor appear in any of these, and these results always hold. And that makes them useful for solving problems. One more thing before we go. The contraction of a 4-vector with itself can also be written as, here's some 4-vector velocity, some 4-vector, and we take the transpose of it, times it by the metric, times it by the vector with itself, so the product of these 3 objects. So for example, let's take the position vector, Minkowski flat space metric, position vector, this is a transpose here. Now here is the position vector, it's a column vector, the transpose is a row vector, the metric, Minkowski metric here, and when we perform that operation we end up with this object here, which we know to be equal to this. Alright, that's it.